Hello, everyone. Welcome to our May edition of Astronomy on Tap Bonn. I'm glad to have you all joining us today. And as always, I would like to remind you that we like to keep it a little bit interactive here, even though we are still only on the computer. So if you want, you can interact with us in the chat, post all your questions to the speakers that you have in there, and hopefully sometime soon we might see you back in the pub where we can interact in a little bit more direct way. And I also want to remind every one of you, participate in our quiz. This is the link to the quiz. So until the end of the second talk, you still have time to participate, and then you might actually win a couple of prizes related to astronomy. And also, I hope the quiz will be a lot of fun to work on. So what do we have today for you? We have two talks today. So we have Andrea Gokus from the Sternwarte in Bamberg of the University of Erlangen-Nürnberg, and she will talk about blazars, and she will tell you what they are, and she will tell you how they really show you the variable high energetic sky. So I'm really excited for this talk. And then we'll have a slightly related talk by Dr. Felix Pötzl, who you might already know from a previous talk, from a previous events. He's usually our brilliant moderator, but today he will actually talk about his own science, talking about magnetic fields at the edge of space and time. And then we'll present the answers to the quiz. So, looking forward to a great event today. And as I said before, of course, interact with us in the chat. And as always, you can also interact with us on social media anyways. So, without further ado, I'll give over to our moderator for today, to David, and to our first talk. So, have a lot of fun.
And as you said, I'm your host tonight. In this very special night, actually, we are approaching a total lunar eclipse. And unfortunately, we can't see it from Europe, but the weather is bad anyways. So the best thing to do now is to watch this event, to watch Astronomy on Tap if you are a space and astro enthusiast. And the topic we have today is somehow related to the total lunar eclipse, because so both things, the topic and the lunar eclipse, it's about something dark and mysterious, but also very bright. So I hope you all know that lunar eclipses only occur during full moon, which is quite a bright thing. And today we are talking a lot about black holes, and especially supermassive black holes, the active galactic nuclei, which are dark, but also the brightest objects in the universe we know about. So, as Laila already mentioned, our first speaker is Andrea. And yeah, I'd like to ask you how you actually became an astrophysicist and why.
So I became an astrophysicist by simply studying physics and then focusing on astronomy-related topics during my bachelor and master thesis. And the idea I kind of got while watching Star Trek with my family when I was a teenager. Well, so this was the first connection that I got to space, and that something is there beyond our solar system. So that's how I got interested. And then I became a little bit of a nerd and watched lots of documentaries, read research or books that were written for the public from scientists. Yeah.
Oh, I see. And I guess in some of these books, the black holes also appeared.
Sure. Yeah, sorry, the dog said just said goodbye. He has to go for a walk now.
Nice. So why can we actually see black holes? I mean, they're black.
Yes, we can see them by when there's matter close to them, and then when this matter is accreted, it gets really hot and really bright, especially in the X-rays, for example, and that's how we can detect them. but only
Okay.
when they're interacting with some matter or some stars.
Cool. I guess you will go into detail in your talk.
Yes,
so you're
very
not
much.
only a scientist, you're doing your PhD, but you also engage with the public, and you give guided tours at your workplace. What's the most interesting point of your workplace?
It's an old building, an old observatory that was built in about 1890, and we still have functioning telescopes, actually good telescopes there that we use also not only for just watching the sky with the public, but also for actually doing astronomical images and training students that come to the observatory twice a year for our lab. And yeah, we have cool stuff. We have old telescopes there. We also have a few meteorites that people actually can hold in their hands. Yeah.
Nice. So I'm looking forward to your talk, and I have a dog also here who's watching and checks the chat. So whenever you have a question, just feel free to ask, and I may interrupt Andrea and ask it for you. Okay, so the stage is yours. Feel free to share your screen. There it is.
I'm on it.
And full screen. Perfect.
Okay, so thanks for spending the evening with me. I'm excited to be here and to talk a little bit about the research that I'm doing my PhD. I know the title is quite long. There are lots of different topics in there, but don't worry, we will entangle them one by one. And I say we just start with the objects that I'm studying, which are blazars. So what is a blazar when I talk about this? So David gave already a mysterious introduction. Blazars are a special type of active galactic nuclei, or AGN. And those reside in active galaxies. And what makes a galaxy active is actually that there is a supermassive black hole that feeds on matter. So all galaxies, as we know so far, have a supermassive black hole in their center. And when I say supermassive, I mean masses of 1 million to 1 billion solar masses. So these things are huge and very heavy. And when they have matter close by and the matter interact with the gravitational field of the black hole, we can have accretion. So this is an artistic impression of what we think it could look like inside the center of a galaxy when we look at this active nucleus. And we have the central black hole, but compared to the size of the whole AGN, it's quite small. So you can't see it here, and it is outshined by the accretion disk that is surrounded by it. And this accretion disk is, it's hot plasma that is falling slowly inwards towards the black hole and falls onto it. And by this mechanism, a lot of energy is released. And in order to remain active, such a million or billion solar mass black hole only needs to eat about 1 to 2 solar masses or sun-like stars per year. So that is actually not much compared to the overall size and mass of the black hole. So these are the innermost components, and then we have a little bit further out, or well, actually up to one light year approximately or more, we have a dust torus that can block the side view when you look from the side into the inner region. This is colder dust and matter. And then only in the case of about 10%, an AGN also produces a jet. And a jet is this long collimated outflow, and this can become really, really large, that it is even larger than the galaxy around this active around its nucleus. So these things can become huge, and they emit a lot of radio emission. And when so this is basically, one of these radio loud, that's why we call them radio loud, when they have a jet, lots of radio emission. This is 10% of the AGN. But this is not a blazar yet, because there's a difference in how you view these objects. So, and if you, as an example, if you view this from the side, as you actually do now with a picture, you can see both jets going up and down. You can't really look well into the inner region, and this then is called a radio galaxy. So this is not the phenomenon of a blazar, but a blazar is when we actually have the jet pointed towards us. So we look into the jet. That makes them appear quite point-like, and also has very interesting effects, because the matter in this jet, that is particles moving close to the speed of light. So they're super fast. And since this jet is pointed towards us and the particles are moving towards us, several relativistic effects happen, and relativistic boosting causes, for example, that these objects appear brighter actually than when you would look from the side. So that's a special thing about these blazars, and this will play a big role later on when we talk about when I will talk about what I'm studying with them. So I also mentioned, so these are the blazars, and I also mentioned the high energetic view. So what do I mean with a high energetic view? Blazars emit across the whole electromagnetic spectrum. I told you already that the jets, for example, produce lots of radio emission, but they also emit from infrared optical light that we can see by our eyes, up to X-ray and gamma ray energies. And gamma ray energies, gamma ray light is the highest energetic light. And what I'm talking about today, the high energy range, then I will talk about X-rays and gamma rays, because that is the regime that I'm mostly working with actually. So what does the sky look like at these high energies? This is an image of our whole view that we have when we look out into the universe in the optical with our eyes. This is a picture put together with Gaia data. And what you can clearly see, or what dominates this picture, is the galactic plane here. You see this stripe of light, and then these dark cloudish things, which is just dust clouds of the Milky Way. And then you can see down here, you see the large Magellanic Cloud and the small Magellanic Cloud. These are smaller companion galaxies to the Milky Way. And then the rest, you see several galaxies, but they are very, very small compared to the structures that you can see here. Now, if you look, or if we go to higher energies, to the X-ray sky, it looks like this. This image has just been released last year by the Erosita collaboration. And I will talk a little bit more about Erosita later on. And what you can see here now is, again, there are lots of bigger, larger structures, especially these spurs, emission that is coming from our galaxy, from probably the central region. You have, for example, here is a very bright X-ray binary, and then on the right here, this larger structure is a supernova remnant. You can also see the large Magellanic Cloud down here. But these are all galactic sources, and I wanted to talk about extragalactic sources. And if you look closely, you have lots of white points all over the place. Especially, you can see it very well above and below the galactic plane in these reddish regions. These look like stars, but they are actually not. These are all active galaxies. So not blazars in particular, these are all active galaxies. And within this picture are about 100,000 AGN. So that's a lot. And when we go to gamma rays, so now we will, I mean, I will want to talk about blazars, but let's keep it with the AGN for now. This is now a really large sample of AGNs that we see in the X-rays. And if we go to even higher energies, the gamma rays, it shifts, this view changes a bit. Again, you can clearly see the galactic plane with diffuse gamma ray emission and some pulsars. But you can also see again these several point sources that are red around it in the border, and then wider, a little bit whiter in the middle. These are all also AGN, but now in the gamma rays, a large fraction of those are actually blazars. And they're just not only sitting there, but they are very variable. So now we're coming to the variable part of the talk. So what blazars, a very unique feature of blazars that is very prominent is their variability. What do I mean when I say variability? Maybe you've never heard of that, no worries. So when a source is variable, let's just keep it with a very broad definition that it doesn't show a constant flux over time. So it basically isn't as bright, always as bright as it used to. It can become a lot dimmer, it can become brighter. So this is constantly changing, and especially blazars are very variable, which has also to do that with the fact that the emission is actually relativistically boosted towards us because of the jet pointing towards us. So how can we find out how if a source is variable, right? So this is, I mean, I can now say that this is the case, but how actually do we know this? And basically what we have been, or what the scientists have been doing in the last few decades is observe several sources continuously and study this variability, not only for blazars, but also other sources. And we do this by just measuring the energy or the flux that comes from these sources over a period of time. And basically we call this monitoring, right? So the best is that in best case, you constantly look at the same source. The problem there is that there are not many monitoring facilities available. Usually people have, or the telescopes are looking at a smaller sample of particular sources, but more often for those, but there, since I mean, I told you the numbers, right? There are 100,000 AGNs or even more out there. You can't really look at each of these sources with just one telescope. So one chooses basically a sample that for either the most interesting sources or the most variable one, but this actually introduces a bias in our research. And how this scientifically how this looks like is with a light curve. So this is just a drawn example. You have on the x-axis, there is the time, on the y-axis, there is the flux, and if a source is just wobbling around and showing a different kind of different states of activity, basically this just flickers around. However, what makes blazars are not only that kind of variable by just flickering around, they can also show outbursts. So when their flux can increase by up to 2 magnitudes in the gamma rays and or in the X-rays. And so we have something that we call a blazar outburst or a blazar flare. So there is an increased flux over a short amount of time, and that actually can vary for different sources and also different flares, actually, that the flux changes very fast within hours and stays at this high flux only for a short amount of time, hours or days, but also outbursts have been observed that take a couple of weeks actually to be over. And how a light curve with a flare looks like, that's an example here. So there's really this huge increase over a short time. And if you have a very, very dense monitoring, you can really observe this nicely. If you would imagine there are just, I don't know, 5 data points in the light curve, then maybe you would either miss the flare or not properly see how it increases and how it decreases at all. So dense monitoring is, in case of studying variability, always a good choice. So how do we do that? And there's one unique instrument which is called was the Fermi satellite, and then on board there is the Large Area Telescope, or LAT. It's shown here. And so this is actually the satellite that took this all sky image that I showed you before of the gamma ray sky. And as I told you, there are most of the sources, the extragalactic sources that Fermi-LAT sees, are blazars. And these are about 2,800 blazars that the Fermi-Lat collaboration found over the years. And in the same coordinate system, here's the sky where all these sources are located. Also here I have the number. So among all these AGN that are detected at gamma rays, 98% are actually blazars. There are a few exceptions, but most of this is totally dominated by blazars. And Fermi has done this by continuously monitoring for more than 10 years now the sky. It scans the entire sky up to 3 times a day. And so that means that you actually each day you get an image of the gamma ray sky and can look at your favorite source, what it's doing. So this is really a unique opportunity since 2008 when this satellite started. And what Fermi found was that there are actually different kind of these blazar outbursts. As I already mentioned, some are shorter, some are longer. Then you have very short time variability during even a flare. So that means that not only does the flux increase a lot, but also during that it shows that the flux can vary within this flare a lot. So that covers the gamma ray sky at the moment. And then I also wanted to talk about X-rays and Erosita. And Erosita is a new X-ray telescope that scans the entire sky as well. It's a German-Russian mission that's just started in June 2019. And you can see this artistic impression here. There's also another telescope on board Erosita. No, Erosita is the telescope. And it doesn't have the same technique to observe the sky as Fermi, because it while it rotates and moves around the sun over time, it scans the entire sky once every 6 months. So the X-ray image that I showed you before, the all-sky image, that was done by one of these one full sky scans after 6 months. And as you can already see a little bit, so this is taken from an animation of the DLR promotion video. So if you're interested in that, you can just go on YouTube and Google Erosita DLR, and then they have a very nice short video explaining how the mission basically is, what the mission consists of and how the observations actually take place. And at least each point of the sky gets visited by the Erosita once every 6 months. But on the poles here, that's why it's a little bit brighter here, you can observe your sources quite more often. So it depends a bit on the region of the sky, how dense the monitoring there is, but at least every 6 months.
Okay, Andrea, we have a question. We are already on the technical observational part of the talk, but it's a question on the physics actually behind the jet emission, the bipolar jet emission of AGNs. Could you comment on that?
Comment on the emission of the jet.
Yeah, so what's the physics behind the jet emission?
Okay, I actually will come a little bit later to that, but I can already tell you that you have, especially at the high energetic, so you have the emission is made up by synchrotron emission and also inverse Compton emission and maybe proton synchrotron emission. So I will tell this actually later. I have one slide with a little bit more scientific details just at the end. So they also have a plot that I can use for explanation. So maybe that's better to do it.
Let's hope we get to this very rich physics at the end of your talk. Another question is if there's one of the most prominent blazar or most popular blazar, or if you have a favorite blazar.
So there are actually, there are a few blazars that are more or less famous. So they have some cryptic names, but like 3C 278, 279, or Makarian 421. And actually Makarian 421 is it's the closest blazar that we have, and I'm also working on that source as well. So yeah, I wouldn't say they're my favorite, but there are a few that have been studied more, and this is actually also due to the bias that that we tend at the beginning. They tended to look at the brighter and more variable sources, and now with more unbiased monitoring, there are actually other interesting sources out there, but one has focused in the past decades on a handful of sources. I would say there are some that have there's so many papers about them. Yeah, and actually regarding, so I can jump back to my talk actually again. So regarding Mercurian 421, it's actually a bit sad because the Erosita sky is not, the data of the Erosita sky is not fully available for all members, because, so as I mentioned, it's a German-Russian mission. And at the moment, the situation is that we have a German half of the X-ray sky and a Russian half of the X-ray sky. And Mercurian 421 that I'm working on is on the Russian side. So that's a bit sad. Yeah. So this is the German half, right? So you can here, this is again a part of the X-ray image that I showed you before. And I want to talk a little bit more about what kind of project we are currently doing, since this is a new mission. So within the first scan, among these 100,000 AGNs, we found about 8,000 blazars or blazer candidates. So that's also a lot compared to the sources detected with the gamma ray satellite Fermi. That's actually a smaller number, because if you remember, it was about 2,800, but for the full sky. So there are a little bit less blazars that we actually see in the gamma rays. So, and now with Erosita, for example, it's possible to really study this large sample of blazars. Before, one really had, there was an X-ray mission called ROSAT, but this had been a long time ago, and it was not near as sensitive enough as Erosita. So there were not so many blazars observed by ROSAT, but now we have the possibility to do a really large sample study on all this data that we get. And as if you remember, we have at least one flux measurement every 6 months, so we can really study the variability over a long time, at least 4 years. And for the brightest sources, there will be even a possibility to study the intraday variability. So there again, we go for the brightest sources, but this is just since the limitations of the sensitivity of the instrument. So it's always easier to study brighter sources, right? And what we're also planning is we want to now combine the X-ray data that we have and also the gamma ray data from Fermilab for a full high energy analysis on the variability of blazars, and see if there are connections and correlations between both energy regimes. So I also talked to you about the flares, right? So now this one part was the long-term variability, but we also have this really short-term variability. And I want to talk a little bit of how we can detect that with an example of our Fermilab satellite. And since I mentioned Fermilab views the entire sky, you have a full sky image every day, right? So you can look at each source every day and see if it's detected, how bright it is, etc. So we actually do this in the collaboration. We have shifts where we analyze the data every day. One shift lasts usually 1 week. And so now if we know the usual flux of a source, since the sky has been monitored for over 10 years now, we can, when we downlink the data and analyze it, we can, if we find a current flux that is very, very bright, at least a factor of 10 brighter than its usual flux, we usually speak of a gamma ray flare. And that's when things get interesting. And we want to report this to the community, actually. And we do this, for example, we have something we call Astronomer's Telegram. So this is like a short notice thingy where we send out this notice that a blazar or also other interesting sources, of course, have been observed. And the astronomical community can decide whether they want to perform follow-up observations on their own. So, for example, if you see, it's quite usual, for example, if we send out an astronomer's telegram about a gamma ray flare of a blazar, that there are some follow-up observations, for example, by optical optical observatories. But you can also request these observations yourself. And this is, for example, what I then did during a flare that actually led to my first author paper. So we can ask for follow-up observations ourselves in all of the energy regimes. Now, why is it interesting, or why am I asking for so much data, right? I mean, you could ask, it's just the gamma ray flare, just analyze the gamma ray data. Well, the blazar emission covers the whole electromagnetic range, as I said in the beginning. So if you want to have a look at these sources and understand what they're doing, we really need the multi-wavelength view. And now we get to the very scientific part at the top of the talk. So this is an example of what we are actually doing for our sources when we see a flare, and what we do with the multi-wavelength data. We put this together, all this data, in a spectral energy distribution, or SED, and that looks like this. So now this looks, probably there's lots of information there. Let's quickly go through this. You can ignore for now the y-axis. This just shows how bright the source is, basically the flux level. And then in the x-axis we have the frequency, and that actually goes from radio up to gamma rays. Now the green data in here, that's archival data that has been taken at one point at a time just in the past. And then we have data in these black data here, which are simultaneous, so taken at the same, more or less at the same time. And this is an example for an SED just doing a usual low state, right? The blue line, I will come to that in a moment. And now if we have a flare, we can again also collect our data, and then you can directly see that this the shape and the data points, they have changed, and especially increased in the gamma ray. So here you can really see your gamma ray flare that was observed with the Fermi LUT. And XRT, by the way, or XMM, those are X-ray satellites, and UVOT is observing in the optical and UV range. So what are we doing with these data now, and what is the blue line? The blue line is our physical model that we try to fit, or that we use to explain the observed emission that we have here. And as I said before, the variability of these blazars is sometimes very short. So the more simultaneous the data, the better, because the more you look at the source at the same time at all the frequencies, the better you get an image of what is going on. However, what is happening here in these, during a flare, there are several theories still how such a flare can be produced. And possible explanations include, for example, interaction of the particles with a shock front in the jet. There could be turbulences in the jet. One can also find a connection to something happening in the accretion disk, for example, an accretion event where much more matter gets accreted at the time, or also preceding mini jets within the main jet. So the emission, coming back to the question that was asked, the emission that we see from blazars is very dominated by the jet. And these two peaks, here are prominent for blazar SED. So these are very typical. And you have this lower energy bump. This is synchrotron emission by electrons. And this higher energetic bump that in our case, in our paper, we explained it with inverse Compton effect on external photons. When electrons scatter up photons and push them basically to higher energies, there are also other explanations, for example. So one can also distinguish where the photons come from that get upscattered. There are also models that include protons. So this is a purely leptonic model, only explaining stuff with electrons. So yeah, I'm not going further into detail. If you have a more detailed question, you can ask it. But because I want to finish now. So what have we learned today, and what can we, as astronomy interested people, look forward to? So we learned that blazars are active galaxies that have a jet pointed towards us. And because of the jet pointing towards us, we have relativistic effects, and that makes the blazars appear quite bright, also very variable. And blazars also can show these strong flares or outbursts. The cause of the outbursts is not completely understood. So this is an actual topic of research at the moment and has been for quite some time. And we have great instruments. For example, in the last decade, Fermilab has really pushed forward discoveries and new insights into the gamma ray emission of the universe. It's not only blazars, also galactic sources. And now we can complement this with Erosita data, X-ray data, since that satellite was launched in 2019. So we have new discoveries, especially also made by Erosita, and new insights to be looked at, to be looked forward to in the near future. And if you like this talk, and if sometimes I tweet about this, so you can follow me on Twitter if you want to. Sometimes I also tweet cute pictures of my dog if you like that. I have also written a little bit more in detail about the projects that I have been doing in the past and I'm currently doing on my website. So you feel free to check that out as well. Thank you.
Yeah, I will. Thank you very much, Andrea, for the overview and the deep insights into the physics of AGN. There was another question, quite basic one. So it's about the number of jets. If there's always one jet or if it's two jets, and could you say something about that?
So there are always two jets produced. Well, this has something to do with conservation of energy and momentum. So, but actually, when you look at blazars, you can resolve the image of the jet, and I think you probably had some talks on that already at Astronomy on Tap here. But for blazars, you actually only see the jet that is pointing towards us, not the one that is pointing away from you, which has to do also with the relativistic beaming. So for blazars, they appear just once, that they are one-sided jets, but from the physics part, there must always be two jets. What can also happen, or what has been found, is that sometimes, I mean, an AGN could have different cycles of activity. So it can switch on, be active for some time, switch off again, and then in the meantime, when a new jet emerges, then it could point in a little bit different direction, such that you find weird structures, especially in the radio emission.
Okay, thank you very much. So it's the conservation of angular momentum, which explains, among other things, this appearance of AGNs. Thanks. So let's get the second speaker on stage. So Felix, if you want to unmute also. So you,
Yes.
hi, you do research on AGNs as well. And
Yeah, exactly.
I would like to ask if you see Andrea as a competitor or as a collaborator.
Especially in this case, much more of a collaborator, especially since I work with low frequency radio data, and to get the full picture of AGN, we really always need to work with all the frequencies. But being an expert on all the frequencies and all the physics is really difficult. So it's good to spread the work up.
Okay. Do you agree, Andrea?
Yeah, sure. I mean, so I mean, maybe, yeah, I don't think that career-wise, there's always at some point some fight because there are not so many positions. But science-wise, I have not had much experience with lots of sorry, what was the English word again?
Competitors, collaborators?
Yeah, thank you. Lots of competition, because I mean, I analyze these blazars with multi-wavelength data, so I have to work together with lots of people. Yeah, and these large collaborations actually, I think, make it easier to work together and not be competitors.
Okay, that sounds very friendly. Just one short question, maybe short answer. Can gas clouds in the line of sight be the reasons for the variability of blazes?
If it's meant that it just blocks the view, then no, because from blazers we basically just see the jet and we look directly into the nucleus. So if you view the AGN from the side, then you have these gas clouds, this dusty torus that can have an influence on that. However, there's also an explanation or an idea that, for example, a gas cloud can enter the jet and then gets sheared up and can also produce the flare with this, but not by obscuring it, but by introducing more other material into the jet and creating turbulences.
Okay, that was a very clear maybe. Thanks. So you can relax now, and we go on to Felix. So it looks like so you were born near Bonn and you studied here in Bonn. You did your PhD in Bonn, and now you're a postdoc here in Bonn. Do you ever leave this wonderful city of Bonn?
Well, I really like it here, as one can see, right? But of course, I would like to move to some other place at some point. And it's also really fruitful to do that in science and like work with new people, for example.
Okay, so you can share your knowledge with people all over the world, and these people can ask questions. Feel free. You can also ask them in German, and we will translate into the language of science, which is bad simple English. Felix, your turn.
All right. Can you see my screen?
Yeah, you haven't started the presentation yet.
Yes, it's full screen now, right?
Yeah, now we go. There we go.
Okay, perfect. Then I go. Yes, so the title of my talk is Magnetic Fields at the Edge of Space and Time, which I admit is a bit splashy, but you will understand what I mean with that at the end of the talk. So I'm really excited to finally talk about these results that have been published recently in the Event Horizon Telescope collaboration. And maybe you have seen this picture in some other form already, but I will tell you in this talk what is new about it and what is so exciting. So it could be that you have seen this image also on the internet. I just collected some of the memes, and the internet gets very creative with this image, and I really loved what it did with it. Some memes also make fun of the fact that the image is kind of blurry, but this is actually what we observe, and you have to live with the resolution for now, although we really are working on to improve it. So yeah, this is the image that was published in 2019 with 6 papers going along with it. And yeah, it's already been 2 years, but we haven't been idle. We have been working further on this data, and in March this year we published 2 other papers which looked at the data, I could say in a different way. And we analyzed some other part of the data, and now the image basically looks like this. And what I want is you to be able to understand this image at the end of the talk and be able to grasp what it actually means that we see that. It's important to note at this point, since we already talked about collaboration and competition, that this is not the work of only myself, not even like only a small group of people, but a lot of people have been working on this data. And you can see some of them here where we were working at our institute in Bonn in 2019 to get the first images. And then for the next 2 years, we tested and vetted the data and the models again and again. And I will give you a bit of an overview about this process as well. So since we're dealing with magnetic fields, I want to start with some real life examples of magnetic fields that you maybe know. So on the left side, we see a magnet where like quite a normal magnet with these field lines that you can see when you put like these small iron pieces there. And then you can really see these magnetic field lines. And also Earth has a magnetic field. This is shown here. And it actually protects us quite well from solar wind. Without it, life wouldn't be possible on Earth. And we can also use it for navigation. For example, like with this compass. And maybe you have seen magnetic fields, well, not seen them, but they were used in an MRI. So maybe you have been in one of those to take some medical picture of your brain or other parts of your body. And I put here just some numbers to give a bit of context. Like the Earth magnetic field is about 0.5 Gauss. If you don't know exactly what a Gauss is, maybe you know what a Tesla is. These are the units for magnetic field, but only look at the comparison, right? A normal magnet has maybe, that you can put on your refrigerator, has maybe 10 Gauss, and the MRI is like much stronger than that again. Just to give you a little bit of context here. Then again, yeah, we're talking about magnetic fields at the edges of space and time. And of course, I'm talking about black holes here. And yeah, where the left is an interesting artistic expression of this phenomenon. On the right-hand side, it's a bit more illustrative. So basically what a black hole is, if you have a mass that is sufficiently large and also compact, it can form a black hole, which means that within the event horizon, even light cannot escape. If you imagine a rocket that wants to leave Earth, it has to reach a certain velocity to completely escape the gravitational potential. And yeah, while we can actually do that on Earth, for a black hole, this escape velocity is much larger and can even exceed the speed of light. And this is the case within this area that we call the event horizon, and then light cannot escape anymore. This normally happens in 3 dimensions, but this example with the whirlpool and chips quite nicely shows it in 2 dimensions. Yeah, and at some point you just cannot escape the pull of a black hole anymore. Okay, so why are we interested in black holes? Why do we think that they are there? Maybe you heard about gravitational wave detections from LIGO, and there is a lot of evidence around. But one thing that people wondered about is, for example, when these jets were observed. This is the jet in M87, which is actually the galaxy where we observed this black hole. But 100 years ago, no one knew that it was there. There was just this jet seen, not like this. This is a Hubble image, so this came only later. But with this and also other phenomena, Andrea talked a lot about AGN already. They are really highly energetic, and with sort of one of the only ways, really the only way that we can explain it is with black holes, because they can actually deliver the energy that are needed to create this like luminous, very luminous objects. This is here another view of M87, where when we use different arrays of telescopes, we can get much closer and ever closer to what is in the center of this galaxy. And today we'll not go into detail about how this observational part actually works concerning very long baseline interferometry, but you can see lots of other talks about that also on our Astronomy on Tap YouTube channel. So what we want to know is basically what is happening like around this black hole. So Andrea also gave quite a nice overview over this already, right? You have this accretion disk where like particles move around the black hole, like they start to fall in it, but due to the angular momentum, they don't directly fall onto it, but they form like this accretion disk. And magnetic fields play here a huge role because they actually needed to violently expel these particles that then are visible in these jets that was already talked about enough, so I would not go into much more detail about these jets. But keep in mind that magnetic fields are really very important here, so we want to study them. And how do we actually do that? Okay, you may be confused by this image, but let me explain. When I myself attended a lecture on polarization, and I will tell you what this is, I was first shown this picture. And I was like, okay, what does it mean? Well, the man that showed that had a story behind this. Basically, he was at an airport, wanted to know when his flight takes off. And he was looking at those screens, but he couldn't see anything. They were black, like, okay, what happened? And the people around him didn't seem to notice it. So apparently they were not broken or something. And then he took off his sunglasses. Well, it's not like the sunglasses were so dark that he couldn't see anything at all, but it's only that the light from the screens was blocked. And this is due to the fact that the screens emit polarized light, and the sunglasses filter polarized light. They act as a polarization filter. And I want you to be able to understand what this polarization thing is all about. So I will start from first principles and say again, well, you probably know that light is a wave phenomenon. It is an electromagnetic wave where you have oscillating magnetic and electric fields. And depending on the frequency of this wave, we see like a different phenomenon. And here I'll show again the famous electromagnetic spectrum, where we only have the small portion of visible light. And then we have like many other frequencies where we observe. And yeah, we can actually see those active galactic nuclei, Andrea mentioned, across this spectrum. And while she focused on the high energy part, I will focus on the part where we observe in radio, which is more like in the gigahertz regime. So but this oscillation of this electric vector is actually very important if we look at it a bit more closely. I hope you can sort of get this animations here, in the sense that now we have this oscillating magnetic and electric field, which are shown here as red and blue lines. But you can see that this electric vector can not only oscillate in a line, which we call linear polarization, but if we can, for example, also trace a circle while it's using it, then it sort of creates this helix. Admittedly, you cannot see this with your eyes. It's only when you have polarized sunglasses or you have sensitive radio astronomical receivers that can also see that. And the important thing will be this linear polarization, which we can actually detect with receivers. We can build them that they can be very sensitive to that, and we can see in which direction this electric field vector actually oscillates. So why is that important? I will go back to some physics class in case you skipped it, I will repeat it for you. Maybe you remember it. So man basically needs to understand what is the Lorenz force. I put here a simple experiment to set up. I could probably do that even if we were in the pub, but now you have to bear with me with these images here. So basically what we have is a magnet, and we have this small metal bar that is conducting and can conduct an electric current, and it's connected with these cables to the power supply, and we can turn on and off the current here. So when there's no current, nothing is happening. But when you actually turn on the current, then this metal bar will move, and it will move perpendicular to these magnetic field lines between the north and south pole of this magnet that is shown here. So this is really the basic experiment. And I want to give like an anecdote to my physics teacher, who asked us the question, why does the dwarf always have a headache? Well, he put a dwarf on this metal bar, and he was then sort of sitting on a swing. And when he turned off the current, of course, the dwarf would hit his head on the magnet. And this was back then in physics class a very illustrative example how the Lorenz force actually works. So props to my physics teacher for showing us and illustrate it that way. So yeah, you can now pay more attention to this animation on the right, where basically now we don't have a current moving through a metal bar, but we have a charged particle, namely an electron, moving in a magnetic field. And it will also be subject to this Lorenz force, which is like very fundamental in nature. And yet here it's not connected with cables. It's not it's not like this metal bar hold back by the gravitational forces on Earth, but it will move within this magnetic field and it will be deflected. And this deflection, which is also an acceleration, leads to it emitting radiation. This is this light cone that you can see here. And if you look closely in this animation, this electric vector that you see, which is in this wave where the particle emits radiation, will always be exactly perpendicular to the magnetic field. And this is really the key thing that you should understand here, that these electric fields is so polarized in a way that it's always perpendicular to the magnetic field underlying it. And if you didn't get it so far, I have a great video where one can illustrate this a bit further. So consider here this particle is moving around the black hole, and you have this magnetic field lines here. In this case, for a weaker magnetic field, these magnetic field lines are sort of dragged along the particle flow and are like ordered like this around the black hole. And you see these small photons traveling to Earth, and then we can detect them. And their polarization will always be exactly perpendicular to the magnetic field underlying it. And if we just observe this and we observe these electric vectors, they will look like this for the magnetic field that I showed you now. For the stronger magnetic field, it has more like this shape. And of course, we then see exactly the opposite in the electric field that we can actually observe. And then the image will look like this. Of course, there's not only extreme cases in nature. So if we have like an intermediate case, the magnetic field also like has this more bit tangled shape, and we see also a bit of an intermediate case. And this is what it would look like in that case. And if you look back at the image, which I will also display now again, it already resembles our observations quite well. So just showing this a bit more clearly again, where we have different magnetic field configurations on the left, whereas also, for example, a vertical magnetic field, which is shown as the rightmost picture. Yeah, we can from theories predict different things. Our accretion disk, where I showed you the magnetic field is really important also for producing these jets, it can look a bit different. And yeah, astronomers are really good at naming things, as you probably have heard already. So we have two main models for these accretion flows, and one is MAD, and the other is, of course, SANE. So it can be MAD or SANE, where they are abbreviations. And MAD stands for magnetically arrested disk, where the magnetic field is stronger and is like really sort of frozen into the accretion disk. While in the SANE case, it's weaker and more turbulent, more tangled, as you can see on the right. And we want to know like what is happening in M87, near close to that black hole. So
yeah, I really love these acronyms, and yeah, you're doing great. It breaks my heart, but I would like to ask you to come to an end till the next.
Okay.
Is that possible?
I will speed up.
Okay, thanks.
Okay, I will just talk about the modeling. We have, well, we want to, of course, know what is happening, and we need theoretical models to compare that to our data. This is one of those models that you see here, where we can actually closely resemble the image already. But of course, we need several ones of them. And here, we don't have to look at each of them individually, but say we tested a lot of models, like 70,000 model images to be precise, in different configurations of MAD and SANE disks, different black hole spins. Yes, the black hole can rotate and it can actually affect the data that we see, different viewing angles. And from that, we could conclude that M87 is in fact MAD. So this is what we could conclude from comparing all these model images with our data. Also on the left is again the image that I just showed you. The depiction on the right is the different days where observations took place, and the top panel is a bit more accurate representation of the data. This orange image is shows a bit higher resolution than we actually have. And what we know what else do we know from this data what we didn't know before, and not even from the image from 2019? We can say that the MA7 swallows about 1,000th of a solar mass per year. This is much less than what Andrea said about where we can have them swallowing like 1 or 2 solar masses per year. MA7 is a bit of a weaker AGN. That is what we know also now again. The magnetic field strength about 7 to 30 Gauss, which is sort of in the range of your refrigerator magnet, if you remember that. But of course, these are much larger scales here involved. And we know the black hole is slightly rotating, but it's unfortunately not very sensitive to our polarization, so we don't know exactly about that. Maybe I skipped this animation to be short, and I will just want to end with this great video about showing the scales that we actually observe and how tiny they are. I really love these animations. So you see how we added this new structure, which are the electric field that we now observed in this source. And so you can see the Event Horizon Telescope YouTube channel for more animations like these, very illustrative. Yeah, see for yourself. And with that, I want to end. And yeah, thank you.
Oh, thank you so much. This was epic. Thank you to Felix. Thank you to Andrea for these very cool talks. And I hope these demanding times do not drive you mad and you all stay sane.
Mad like M87, yeah.
And with this, I would like to give over to Sven, our quizmaster. And yeah, have fun with Sven.
Thank you.
Yeah, thank you very much, David. Let me just share my screen. I hope this works. So yeah, welcome to this month's online quiz. I hope you have all gone to the form and sent in your questions. Unfortunately, from now on, we cannot accept any answers anymore. We don't have that much time, so let me jump right into it. So we start with the first section, the Astro News, what happened this month in astronomy. And so the first important thing that, the first important thing that happened is that another rover has recently landed on Mars. And the name of that rover is Zhurong. It's probably pronounced differently, but I don't speak Chinese. It's a Chinese rover. China is now the second nation to have managed a soft landing of a rover on Mars. It's supposed to do some ground science. It doesn't really have a robotic arm, but it has some spectrometers to analyze the soil and some ground penetrating radar to look a bit under the surface. So it's definitely an exciting experiment, and we can only hope that we will see lots of results from that one. The second thing that went through the news is that a rocket performed an uncontrolled re-entry this month. And that's always a bit dangerous, because with an uncontrolled re-entry, you don't really know where it's going to land, and so it might land on some cities or some structures, might damage things, might hurt people. So these uncontrolled re-entries are always something that we want to avoid, and that there's probably going to be new laws in the future that prevent that, but as of now, it's not really that clear who is responsible for basically cleaning up their space trash. So this rocket was part of an effort to build Tianhe, or the entire station is going to be called the Tiangong space station. It's going to be the the Chinese space station. It's going to be the third modular space station after the Russian Mir and then the International Space Station. And the Tianhe, the main module of the space station, is the thing that the Chinese flag is on here in this animation. So yeah, there's going to be more modules that are going to be launched and docked with this, but yeah, the main module is now up and in orbit. Yeah, the third question, a probe that has recently taken a sample from asteroid is now finally back on its way to Earth. And we actually had that in a previous quiz, I believe in October. And that probe is OSIRIS-REx. It took a sample from the asteroid Bennu with a target of, well, bringing it back to Earth and analyzing it. Here you can see a nice clip of the sample collection. And yeah, in the end, we want to find out more about the origins of the solar system with this. Okay, the clip does not seem to work, but yeah, it's not that important. However, yeah, that probe now has left Bennu, has left the asteroid, and is on its way back to Earth, and it will probably land in 2023. Okay, that concludes our Astro News section. So we are moving on to the Pictionaries, where we have very talented artists draw a picture of something, and you have to guess what it is. So the first beautiful, blurry picture that you see here was supposed to be the Milky Way. Here you see it in all its glory as actually, yeah, imaged by the Gaia satellite. Yeah, you see the beautiful Milky Way, the band. You see the large and small Magellatic Clouds down here. Unfortunately, you cannot see them from the Northern Hemisphere, so that's a bit sad. But yeah, that was the first Pictionary. And the second one is, well, it's a telescope, but to be more precise, it's a Dobson telescope. And the Dobson design is, well, it excels because it's cheap and easy to build. So this was basically the thing that enabled all these amateur telescopes, that also enabled you to buy a relatively good telescope for not that much money. And the main difference between these Dobson telescopes and professional telescopes is the mount. So you see here, this telescope is just put on the ground. So one axis is just parallel to the ground. With professional telescopes, however, you want this axis to be in parallel to the equator. So when the Earth turns and you want to compensate for the turn of the Earth, you only have to move the telescope in one direction. You only have to turn one of the axes and not both. So these telescopes are much, much easier to build, much, much simpler, but their tracking is just not as good because it's more complicated mechanically. But yeah, they're very, very good for amateur astronomers, yeah, because they enable cheap construction. And the last picture is this beauty here. And I think everyone guessed correctly. This is the planet Saturn. And the, well, very, very interesting feature, namely this hexagon shape at the North Pole. It's still not entirely clear why that is there and why it's so stable. It's a very, very stable form. However, it is changing its colors. And we have been able to reproduce similar shapes in the lab, but it is a bit, it looks a bit weird, definitely, to have this, yeah, hexagonal shape in something that otherwise only has round shapes, right? You see all the rings are round, and, well, everything about the planet Saturn is round except for this one hexagon. So that's quite interesting. Yeah. With that, we go to our last section, the famous astronomers, where we show you pictures of 9 famous astronomers and then ask you for 3, and you have to guess who they are. Here you see our famous astronomers, all of them very, very accomplished in their field and yeah, internationally known at least. or at least most of them. So the first one proved that these weird cloudy nebula that you see in the sky are other galaxies. There was a large debate prior to his finding whether these nebula you see are just some gas clouds in our galaxy or are other galaxies. So alternatively speaking, whether our galaxy is the entire universe or whether it's just one out of many galaxies. And this person, Edwin Hubble, showed that these nebula are too far away to be within our own galaxy, and so that they have to be, their own galaxies. And so that definitely was a very, very big step in cosmology. So the second person constructed a still used catalog of star clusters and galaxies that was named after him. And that person is Charles Messier. He was originally planning to find comets, and I mean, he found a lot of comets. But then he found all these clouds and shapes, and he just wanted to catalog them to not confuse them with comets. And from that, this so-called Messier catalog came out in 1776. And yeah, it's still used to identify some galaxies and star clusters and planetary nebulae. And the last person discovered that stars with varying brightness follow a very tight relation where larger changes in brightness happen over longer periods. So we have some stars that get brighter and less bright again. And this person found out that the more this brightness differs, the bigger the difference between their brightest and their least bright moments, the longer this change takes. And that person was Henrietta Swan-Leavitt. And that discovery was actually insanely helpful, because normally when you look at a star, it's very, very hard to find out how far it is away. Yeah. We cannot measure this with some ruler or whatever. So when we know how bright a star is, we can actually compute how far it is away. And the first person that we had in this quiz, Edwin Hubble, actually used these results to figure out that these galaxies are so far away and that they cannot be within our own galaxy. Okay. That concludes our quiz. I hope I didn't go too much over time. I'm sorry if I did. So let's come to the prizes. Again, how do you win? You just participate in the quiz and you get 50% of the questions correct. Then you enter the winning pool, and from that we randomly draw our winners. We will contact you via email and you can choose from the prizes. So yeah, we have a Metal Earth building kit of the Voyager spacecraft. We have a notebook from the Euclid Consortium annual meeting. We have the book by Brief History from Stephen Hawking, a quiz from Was ist was about space. That one's in German, so only take it if you speak German. And a nice bottle warmer with our beautiful logo on it. Last but not least, we have a Tai Chi voucher, but that you should also only take if you're in Bonn, because it's only valid here in Bonn. Yeah, with that, I thank you for your attention and yeah, for participating in the quiz. And I hope I see all of you next month.
Yeah, thank you, Sven. Thank you, Sven. Thank you to all the fabulous talks that we had today. I learned a lot, because all these blazars and black holes, they're really out of my expertise. So I was really, really glad for these nice introductions into the topics that I heard today. So just to close this event today, I want to announce next month's event. So next month in June will actually be our season finale. So if you joined late today, or if you were wondering whether you should join next month or not, you really should, because it's our season finale, because then we'll have our summer break. And hopefully in the fall, we might resume back in the pub, actually. But before that, join us next month for a talk by Dr. Thaisa Danilovic from the KU in Leuven in the Netherlands. And we will again have a science or fiction game. So if you joined our January event, you might remember there was something there where actually you, the audience, could decide whether the things that we are saying here are true or whether they are false. So I think that will be a lot of fun, and I hope to see you all then. So have a good